Hi, everyone. My name is Maarten. Thank you for tuning in to this part of the EMNLP 2021 tutorial on crowdsourcing beyond annotation. And today I'll be talking about a case study on the SocialIQA benchmark, which is a benchmark that was created to measure the common sense reasoning abilities of models with respect to social interactions. And this was work that was originally done at the University of Washington in the Paul G. Allen School of Computer Science and Engineering, as well as at the Alane Institute for Artificial Intelligence. So given a situation like Alex spilled food all over the floor and it made a huge mess, social intelligence enables us to understand the mental states of others and reason about their motivations and their likely next action. So for example, we can think about what Alex will want to do next after this. And this is in direct contrast to physical common sense, which would be about inferring the states and locations of objects, for example, where the food land or things like that. And social intelligence enables us to say, for example, that after spilling food all over the floor, Alex might want to mop up the mess, and it's more likely than that they will want to run around in the mess. Similarly, social intelligence helps us infer that when Tracy accidentally presses against Austin in the small elevator and it's awkward, the reason why Tracy might have done this is more likely because they wanted to squeeze into the elevator than flirt with Austin. And so the motivation for creating SocialIQA is that models need to reason about social situations to properly interact with us. And humans have this thing called theory of mind, which allows us to make inferences about people's mental states and their next actions. And that we use this ability to navigate everyday social situations seamlessly, as well as even more complex things like courtroom negotiations. However, as I'll show in this work and has been shown by previous work, AI systems today sort of lack this social and emotional intelligence. And part of this is due to the fact that they are pre-trained on large text corpora, which does not necessarily endow them with common sense reasoning abilities, partly due to the fact that reporting bias can actually limit the scope of knowledge that can be learned from static text corpora. And these types of models have been shown to only find complex correlational patterns in training data, and they're not really trained to make sort of inferential reasoning decisions. And so SocialIQA is the first large-scale benchmark to quantify NLP models' ability to reason about social situations. And just as some brief background, this is related to a variety of other common sense benchmarks. And for example, in contrast to the well-known Winograd Schema Challenge or COPA benchmarks, which are more expert curated and small scale, less than 1,000 examples. And these small scale benchmarks can pose challenges for training NLP systems on them. And so in contrast, SocialIQA is actually much larger scale. And then additionally, of those large scale common sense benchmarks that exist, like physical IQA and common sense QA, which are much more factual and cover things more related to physical common sense and physical knowledge, SocialIQA is more in line with sort of inferential social knowledge, in line with theory of mind. And then finally, I should highlight the story common sense benchmark as well, which is about tracking mental states of characters throughout short stories. Here, in contrast, SocialIQA is not necessarily about tracking mental states, but it's more about answering questions, multiple choice questions about everyday social interactions. So in the rest of this talk, I'm going to spend most of the time talking about how we created this large-scale benchmark and specifically focusing on how we can mitigate the challenge of annotation artifacts that we all know plague some of the benchmarks out there. And then I'm going to show some modeling experiments on SocialIQA and specifically showing how BERT and even GPT-3 are struggling to do well on this task. And finally, I'll just highlight quickly that SocialIQA can also be used as a transfer learning resource if you want to do other types of reasoning afterwards. So how do we create a benchmark like SocialIQA? And so one thing we have to think about is our goals when we want to create this benchmark. And so the first goal that we had was that we wanted to make it easy to compare performance of models. And so for that, we're going to think about a multiple choice QA setup. And we're going to also set up a leaderboard so that we can track progress on our task. We also want our benchmark to be challenging. And so for this, we're going to make sure that we use a multi-stage adversarial crowdsourcing pipeline so that our benchmark is not trivially solved by, for example, relying on annotation artifacts. And then finally, because we are trying to measure broadly social common sense reasoning abilities, we want this to cover all types of situations. So we want it to be high coverage and also large scale so that we can train our models on it. And so for this, we're going to use the atomic common sense resource to scale up the type of knowledge that we have. And so just briefly, an overview of the crowdsourcing pipeline that we used. We're first going to take atomic events and embellish them, add names to them. Then we're going to take the events and questions and ask crowd workers to write some handwritten likely and unlikely answers. Then we're going to add some unlikely answers using our atomic-based question switching technique. And then finally, we're going to human validate our questions and filter out the easiest ones. So our pipeline relies heavily on the atomic knowledge graph, which is an atlas of machine common sense. And what I mean by that is a huge knowledge graph that has almost 880 knowledge triples for AI systems to reason about the causes and effects of everyday situations. And specifically, what I mean by that is given an event like X repels Y's attack, as humans, we have the common sense knowledge that allows us to make all sorts of inferences around the situation, like why it happened, how participants feel, etc. And atomic distills this knowledge in triples with 9 different knowledge dimensions or relations. And we represent this knowledge as sort of free text, short natural language phrases. And this knowledge is structured in different ways in atomic. And for example, we can differentiate the knowledge around the causes of the event. So for example, before X repels Y's attack, maybe this happened because X wanted to protect others, or maybe X wanted to save themselves. And before this happened, maybe X needed to train hard or need to know self-defense. But it also distinguishes knowledge around the effects of the event. So after X repels Y's attack, maybe as a result, X will want to file a police report or maybe leave the scene, and maybe X will feel angry or tired, but also maybe Y will want to run home, or Y will want to attack X again, or Y won't feel weak or ashamed. And another way to think about the complex structure of the knowledge of atomic is in terms of what happens to whom. And so specifically, we can think about atomic distilling knowledge about the agent of the event. So here X, the person doing the repelling, versus knowledge around the theme of the event here Y, the person who is whose attack is being repelled. And so as a starting point for SocialIQA, we're going to take one of these events from atomic, and we're going to grab their subgraph with all of the dimensions. And then we're going to select a specific triple, knowledge triple. For example, person X spills blank all over the floor. What will X want to do next? Clean it up. And then we're going to randomly assign a gender neutral name to the different people in the event, here Alex. And then we're going to suggest a question template like, what will Alex want to do next? And we're going to give this as input to a crowdsourcing task, our first crowdsourcing task in this pipeline, where we're going to ask humans to rewrite and embellish basically the context and question. And so given our event, we're going to obtain something like Alex spilled food all over the floor and it made a huge mess. So they made the event longer, added some things, and also filled in the blanks. And then they're also going to embellish the question if needed. In this case, the question was pretty straightforward. So once we have our context and questions, the question now is, how do we collect answers that are plausible and likely and unlikely, or correct and incorrect? And so for this, we designed a second crowdsourcing task where the input was the context and the question, like Alex spilled food all over the floor and it made a huge mess. What will Alex want to do next? And we're going to go to mturk and we're going to ask mturkers to write 2 handwritten correct and 2 handwritten incorrect answers. And so here, a crowd worker, for example, might say that Alex will want to mop up or give up and order takeout after spilling food all over the floor. That's a likely correct answer. And incorrectly, maybe Alex will want to leave the mess or run around in the mess. And so at this point, you know, some of us might think, oh, maybe our benchmark is ready now. We've got our good answers and our bad answers, and we're done. Unfortunately, that's not true. And there's still the problem that handwritten unlikely answers or incorrect answers are too easy to detect. And this is because of this big problem of annotation artifacts. And we know from previous research that models can exploit spurious correlations or annotation artifacts in the handwritten incorrect or unlikely answers. And these answers tend to be a little bit more off topic. They look wildly different from the correct answers sometimes. They can be overly emotional. They can be much more exaggerated, things like that, because there's different levels of how wrong you can be, and there's less levels of how correct you can be. And so typically these annotation artifacts stem from cognitive biases in crowd workers. Again, it's harder to sort of say how to come up with a wrong answer than it is to come up with a correct answer. And so because of these annotation artifacts, this has led to seemingly superhuman performance by large pre-trained language models on a variety of benchmarks. That has led us to the illusion that maybe the tasks or the problems that we're trying to tackle have been solved. However, if you scrutinize the model's behavior a little bit more deeply with maybe some adversarial or new out-of-domain inputs, you'll find that models tend to solve the data set, not the task. And so there's still more that needs to be done. But the question then becomes, how can we make unlikely or incorrect answers that are robust to annotation artifacts that look more like the correct answers? And so what we came up with is a way to collect the right answers, but to a different question about the same situation. And so we'll call this the question switching setup. And here the goal is to find questions and answers that have similar phrasings, but there are clearly answers to a different question, so any human would know what the right or wrong answer is. And so here, again, we're going to use atomic as a way to come up with different questions. And specifically, in order to preserve the phrasing so that the answers look different or look similar, we're going to use 3 different clusters of atomic dimensions. The first cluster is related to needs, intents, and wants. So specifically, what did people need to do before? What was their motivation or intent while for doing the action? And then what are they going to want to do next? Both the person doing the thing as well as others who may be involved. Our second cluster is related to attributes and reactions. So specifically, while X is spilling food all over the floor, how are they perceived, or how would you describe X in this case, which is the attribute? But also, how would X react, or how would others react to seeing this happen? And finally, the last cluster that we're going to use is related to the effects, the involuntary effects that will happen onto both the person doing the event here, X, as well as others or the theme of the event. And so if we consider these clusters, we can sort of have, for one question that relates to, for example, X need, we can switch out X need to a different dimension in atomic and using these clusters. And so this can lead to sort of 2 different ways of conceptualizing the differences between the questions. The adversarial question switching basically ends up switching who the question is about, agent versus theme. So for example, if your main question is about what others would want to do next, then you might end up with question switched answers that are about what the person X would want to do next, which is not really what the question is about, but still very contextually related. And this also sets us up for switching the temporal ordering of the question. For example, instead of asking what happens after, but asking what happens before the situation took place. To be a little bit more concrete, if we take our example from before of Alex spilling food all over the floor and making a huge mess, if we ask what will Alex want to do next, we have our 2 correct answers. We can also switch out the question and say, what happened before? What did Alex need to do before this? And here an MTurker could answer things like Alex needed to have slippery hands or get ready to eat. And then we're going to take those correct answers to that wrong question and then put them as the incorrect or unlikely answers to the original question that we're interested in. So this is the third crowdsourcing part of our pipeline. And if we sort of delve deeper into these incorrect answers, both the handwritten incorrect ones and the question switched answers, we can compare how stylistically different these incorrect answers are to the correct answers. And what we find is that the handwritten incorrect answers are similar in arousal levels using the NRC Canada's valence arousal dominance lexicon. So they're very similar in arousal levels to the correct answers, but they are much more different in terms of dominance and valence compared to the correct answers. So they're much higher in dominance and much higher in valence. But then we can compare the question switched answers. And here, what we find is that the question switched answers are much more stylistically similar to the correct answers across the board. So you might think, okay, now that we have our adversarial examples, our adversarial incorrect answers, the data is robust artifacts. The answer here is almost, but not fully. There's still some things that need to be corrected for with this question switching technique as well. So we're going to do a last step of validating and filtering our data. And here our goal is to sort of polish it up, all of the answer pools, and take the answer candidates that are more robust and have a sort of span a diverse set of answer options. So we're going to select one likely and two unlikely answers from our multiple choice candidate pool. We're going to use NLI entailment scores to do this. Then we're going to run a human validation on the three-way multiple choice question tuples using crowdsourcing to make sure that people can actually answer our questions correctly and that they agree on the right answers. And then lastly, we're going to use a adversarial filtering light technique to filter out answers with spurious correlations. And so the way that this works is basically if you take a whole data set of unfiltered examples, we're going to use a linear model with pre-trained language model representations, for example, BERT. And we're going to use this linear model to basically filter out the easy examples from this large pool of examples. And what this leads us to is a much more robust set of data examples that are that have less spurious correlations. So that's the end of our crowdsourcing pipeline. So now I want to quickly talk about how computational models can hold up against SocialIQA. And here it's a pretty standard setup for measuring performance of our models. We're going to take our full data set of 38,000 questions, split into train, dev, test, and then we're going to fine tune large pre-trained language models like BERT and OpenAI GPT. And pretty standard setup. We're going to take the context, question, and answers and encode them into our BERT representation, and then run a multi-layer perceptron on top and have a three-way classification in that way. And so comparing the performance of all of our fine-tuned models here, obviously random performance on a three-way classification is 33%. And we find that GPT-1 and BERT base do significantly better than random. They're at like 60-something%. BERT large gets up to 65%. And this is at least 20 points below the best, this is 20 points below what humans can do. So even our best fine-tuned model is still 20% below humans. And so this was in 2019, right? And so I wanted to check, how does 2021 models measure up to this benchmark? And so with access to the GPT-3 API, I used the language modeling probing setup in 0 and few shot settings as done in the GPT-3 paper. And I wanted to measure how does GPT-3 perform on SocialIQA. And so as you recall, we've got humans and we've got BERT large that is fine-tuned. And what we find is that GPT-3 35 shot and GPT-3 0 shot perform significantly worse than BERT large. And they're still a little bit better than random, which is good, but we only get 56% accuracy for the biggest GPT-3 model with the most the highest shot prompting that we can do. And so this shows that SocialIQA is not only challenging for fine-tuned models like BERT large, but also in big language model probing setups like with GPT-3. So we can also examine the kinds of mistakes that model make on SocialIQA to gain some insights into what parts of the data make it more challenging. And so I want to give you two examples of situations. The first one is, although Aubrey was older and stronger, they lost to Alex in arm wrestling. And the question is, how would Alex feel as a result? And so we have three answers: ashamed, boastful, and they need to practice more. And we can all kind of guess that here the answer is boastful because Alex just won the arm wrestling match. However, BERT large, fine-tuned BERT large predicts that Alex will feel ashamed. And notably, this is how Aubrey would feel, not Alex, because Aubrey would have lost in the arm wrestling match. The second situation is Remy gave Skylar, the concierge, her account so that she could check into the hotel. And here the question is, what will Remy want to do next? given 3 options: lose her credit card, arrive at a hotel, get the key from Skylar. And so here again, after checking in, of course, getting the key from Skylar makes the most sense. However, Bert here chooses that Remy will want to arrive at a hotel after checking into the hotel, which is clearly what Remy had to do before the situation took place. And so these models here illustrate, or these examples here illustrate the need for better person-centric reasoning, as well as better distinguishing of the causes versus effects of situations. And interestingly, these mistakes kind of seem to align with our question switching dimensions, where we switched out who the question was about, or whether it was before or after the situation. And so we can kind of empirically quantify this a little bit more by looking at the rates of mistakes that models make when they select handwritten incorrect answers versus question switched answers. And what we see here is that the question switched answers are often a little bit better distractors for models, and they tend to be picked a little bit more compared to the handwritten incorrect answers, which is really interesting. So finally, I want to walk you through a little bit of an experiment where we want to teach Bert some more social common sense knowledge. Specifically, we want to look at how SocialIQA can be used for transfer learning. And we're going to use this setup that we called sequential fine tuning, but has had different names in the past as well. We're going to take our Bert large model, then we're going to fine tune it on SocialIQA, and then we're going to fine tune it on our end task. And specifically, going back to the related benchmarks that I talked about earlier, the end tasks that we're going to consider are our small scale benchmarks, like the choice of plausible alternatives, or COPA, as well as the Winograd schema challenge, which again have less than 1,000 examples total. And so focusing on the results on COPA here, the best previous baseline or best previous performance at the time was from Sasaki et al., who reached 71% accuracy on this COPA benchmark. By just training Bert large on the dev set, you get up to 80%. But then if you do this sequential fine tuning on SocialIQA and then on COPA, you can actually reach a new state of the art of 83.4% at the time. And so this is showing, we see similar improvements on the Winograd schema challenge dataset as well. And this is showing that SocialIQA can maybe endow Bert with some social common sense reasoning skills. So finally, to summarize some of the takeaways here, I walked us through the SocialIQA benchmark creation. Specifically, this benchmark is for social common sense reasoning. And I specifically detailed how we had a multi-stage pipeline, crowdsourcing pipeline, where we tried to minimize annotation artifacts, specifically using question switching techniques to ask about different aspects of the same situation. And we showed that it remains a challenging benchmark for computational models, even for GPT-3, which is exciting. And also showed the usefulness of SocialIQA as a resource for transfer learning on COPA and the Winograd schema challenge. And so the data is available on this website. And you can also check out the leaderboard if you are interested in working on this. And of course, I want to give a shout out to my co-authors without whom this work wouldn't have been possible. Thank you so much for listening.